class, I want to take a couple minutes today and give you all an introduction to symbolic logic. So, symbolic logic basically traces its roots to the late 19th and early 20th century. Guys like George Boole and De Morgan and people like that, names that you'll meet up with later. John Venn of the Venn diagram fame was involved, but it really takes off with the work of Frege, a German philosopher, then Bertrand Russell, a English philosopher, and Ludwig Wittgenstein, an Austrian philosopher who spent most of his life living in England. So I don't want to get too much into the history, but I just want to sort of place it. So we're very far from Aristotle, both in terms of the time, but also in terms of the content. Remember, Aristotle's logic was sometimes called a categorical logic. It dealt with categories or classes. Symbolic logic is a propositional logic, which means what it's mainly concerned with is propositions. And the obvious question is, well, what is a proposition? Roughly speaking, you could say that a proposition more or less corresponds to what in grammar we call a simple sentence. Something like, the wall is white, or the trash can is green, right? Those are simple sentences, as opposed to complex sentences like, the trash can is green and in the driveway. That would be a complex sentence or a complex proposition. So a proposition is essentially a claim that such and such is the case, or that such and such is not the case. And modern symbolic logic is a logic that's concerned with the relationships between propositions. In the symbolization that we use what's called sentential logic, or also propositional logic, which is to distinguish it from later iterations of symbolic logic, such as predicate logic, modal logic, and things like that we won't get into in this class. So in the symbolization, the capital letters stand for propositions, or in the language that Wittgenstein and Russell often used, atomic propositions, which is to say a simple proposition of making only one claim that such and such is the case. So if you had the capital letter A, that stands for a proposition. If you have the capital letter B, that stands for a different proposition, right? Or two different atomic propositions. Following that, about 5 symbols are introduced that allow us to combine these propositions into more complex ones, such as what we could call a complex proposition or a molecular proposition, if you want to use Wittgenstein's language. So the symbols that we have, and this is sort of what the symbols that make symbolic logic symbolic, are the dot, the sideways horseshoe, the 3 lines, the tilde, dot, sideways horseshoe, 3 lines, tilde, and the V, the vel. Right, so these symbols basically stand for what are called logical connectives, and the tilde, which means not, and this is perhaps the simplest one of them. So tilde A, just read that as not A or negation A. The V goes between 2 letters. It never goes by itself. And all of the subsequent connectives that I'm going to talk about will go between letters. So A, V, B, you're going to read as A or B. So that it's a complex proposition, A or B. A dot B, you'll read as A and B, because the dot is the conjunction. A sideways horseshoe B, you'll read as if A, then B. And I'm going to warn you that the conditional, is the most complicated and interesting of the logical connectives. It's the one that has caused logicians the most anguish and also led to some of the most interesting results in the history of logic. We can't get into it right now, but there's the truth table that defines this, which you can read about in the PowerPoints and things. While at one level it makes a certain amount of sense, ultimately can lead to a number of paradoxes and strange results that logicians have tried to sort of wash away. But what they've always found is that in trying to wash those away, we end up with things even weirder. And so, but it's not going to come up in this class, but I want you to know sort of lines of research in cutting edge work in logic that you can sort of begin to tap into just by thinking about some of the strange behavior of the conditional. And then finally, you have the 3 bars, which is the biconditional, which you'd read as if and only if. Now, all of these symbols can sort of be defined in 2 ways. In sort of ordinary language, when I tell you, well, read it as and or read it as if and only if or whatever, I'm just using, ordinary English language to define the terms. Ultimately, however, that is not what these symbols mean. The actual official definition of the symbols is given via the truth tables. And there are PowerPoints and things about truth tables that you've got to take the time to figure out and understand. Because there are certain things about symbolic logic that you will not understand until you've sort of digested, absorbed, memorized, and become one with these truth tables. Because those truth tables are the meanings of the symbols. The words that we use to talk about them are not what they mean. There are, although it's sort of a rough and ready way of sort of indicating things, there are crucial differences. So, for example, if we think about the word and, so as in like A and B, that's actually somewhat vague. There's at least 2 different kinds of meanings to the word and. There's I guess you could say the simple conjunctive meaning, where A and B means the same thing as B and A. But there's also the ordinal meaning of and, where we're using and to put things in order, where if I say ordinal meaning of and, if I say he broke his ankle and fell down the stairs, that is a slightly different image than if I say he fell down the stairs and broke his ankle. In the first case, you imagine someone, or in one case, you imagine someone falling down the stairs, and at the end of that fall, they break their ankle. So the falling down the stairs causes the broken ankle. In the other instance, you imagine them breaking their ankle, and that causes them to fall down the stairs. It's a very different scenario. So it's important for us as logicians to have a more precise meaning of the word and, because and in ordinary language can have a number of different meanings. That's what the truth tables are for. They give us sort of logically, mathematically precise meanings of these operators that we will then use for the remainder of the semester. So I want to close out by saying, to summarize, right, this is a propositional logic. The propositions are rendered as capital letters, and then we form complex propositions out of the simple propositions by combining those capital letters with the 5 logical operators. The 5 logical operators can be given sort of rough and ready, ordinary language definitions or meanings, but ultimately to understand what they mean and how they behave and how to use them, you have to get down with the truth tables. And finally, sort of lastly, another reason you want to get down with the truth tables is because once you memorize those 5 truth tables, we can then go on to do truth tables to do other things like classify different kinds of sentences and arguments in different ways, ultimately prove validity and invalidity of arguments and things like that. So truth tables are really going to be the backbone of a lot of what we do. And even when we're not using truth tables explicitly, we're still implicitly relying on them.